in this next section, we're going to still be using derivatives, but we're going to be using them in word problems. And so I know there's a whole lot of stuff here, and you can go back and read this in your time, but basically one of the biggest applications that we have with our derivatives is with optimization problems, and where we're looking for a way to maximize our profit or minimize our cost or maximize the volume that we have available to us or area that we have available to us, or minimize the usage of material, etc. So there's so many different variations that we can do it, and we're just going to focus on a few of them. What we are going to touch on is just minimal in terms of the different types of or styles of problems that you can optimize. We'll start with a basic area of a garden question, and we're given the information that we have. We're going to construct garden, or we have a garden against a rock wall, and we want to fence it in. We want to fence in the three sides that are not with the rock wall using 100 feet of wire fencing. And so we have to figure out the dimensions that we're going to use that would give us the maximum area for gardening. And so we have two things kind of going on here. First of all, the thought that we have to maximize our area tells me that the function that I'm going to be taking the derivative on is the area, because I want the maximum area. But then I do have to consider this connector in here, the fact that I'm going to be using 100 feet of wire fencing. And where does that come into play? Well, that's going to connect my two variables. At this point, if I'm going to maximize, if I'm going to optimize, I would want to take the derivative to find the maximum location, like we did in our last chapter. Our maxes, our mins, our relative extrema. But at this point, I don't have a way, I haven't learned a way to derive multiple variables. You'll learn that in calculus, but right now we haven't. So what I need is this connector, and this connector is what's going to allow me to write either y in terms of x or x in terms of y, so I can create a function that has only one variable. Because I put this as a of x, and you don't have to put it as a of x, but because I did, what I want to do is figure out a way to get rid of the y. And so if I take this connector x plus y plus x, I can write that as 2x plus y equals 100, and then I can subtract the 2x and I get y equals 100 minus 2x, which means that I can substitute 100 minus 2x in for y and create an equation or a function that only has one variable. So I'll do that. My a of x is now x times 100 minus 2x, and I am going to, I could either do a product rule when I take my derivative, because the whole point, maximum, mins and maxes, is taking our derivative, or I can distribute this first. I'm going to distribute it first. So a of x is 100 x minus 2x squared, and a prime is what I want to solve here. So I get 100 minus 4x. Now, if you recall, when we were doing that, to find our mins and maxes, we took our derivative and we set it equal to 0. So I'm going to take my 100 minus 4x and set it equal to 0. And then I can solve for x, and that should be my value, either a min or a max. And in this case, I'm hoping it's a max. I'll have to check to see, but I get negative 4x equals negative 100, and so x equals 25. I'm going to check and make sure. I'm going to do an A prime chart at 25, and I'm going to do some test points. Now I have to be reasonable. It talks about our having a closed bounded interval up on the top. A closed bounded interval means that I have to be careful with my test points, basically, or my endpoints. Obviously, I'm not going to have a garden that has 0 dimensions, because I wouldn't have a rectangle, and I'm also obviously not going to have, I can't have it over 100, because I only have 100 feet of fencing. So that's what that bounded part talks about. And so I'm going to pick reasonable values. I'll pick 1 and plug it into my derivative. 100 minus 4 times 1, that's a positive value, which means this is increasing. And then I'll pick something on the other side of 25 Remember, it's got to be less than 100, maybe 50. 50 would be an easy number to put in there. So I have 100 minus 4 times 50, and that is a negative, because it'd be 100 minus 200, which makes this decreasing. This is, in fact, a max. And so I would say that my x dimension, because that's what I solve for, my x is 25 feet, is 25 feet. And my y dimension on my picture here is going to be 100 minus 2x, so 100 minus 2 times 25. That, again, came from up here. That was the connection I used for y, and I need both dimensions. 100 minus 2 times 25, or 50 feet. So I would say my dimensions are 25 feet by 50 feet. We have a similar problem for you to try. Again, go through it and give it a try on the back side. The only thing that changes, it's the same scenario, the only thing that changes is we're using 200 feet of fencing. So you're going to kind of go through that process the same way and see, pause the video, come back and check your answer when you're done. I hope that picture up on top didn't bother you when you went to the next page. This was just kind of graphing the scenario and showing that our maximum x value is 25 feet, and then working through sort of talking about what it is, what the function looks like, etc. But if you worked through exercise 1, very similar to example 1, the only thing that changed is our 200. Went through that same process. As I worked through, I found that I would end up with x being 50 feet and y being 100 feet. So I have a 50 by 100 foot garden that I would be working with. Now, if it asked me to find the area of the garden, like what is the area, determine the maximum area, which is what I wanted to do on the last one too. Did it say find? Oh yeah, this one just said, this question, the original question said, we want to determine the measurements that would create the maximum area. But I didn't answer what was the maximum area. I got to go back to that. What is the maximum area? So the area is 25 times 50, which would be 1,250 feet squared. So I neglected to answer that. Be careful to make sure you're answering the question. So when I go back to this problem, determine the maximum area, I need to go back to these problems here, and my maximum area again is going to be my area is 50 times 100, and so my area that I'm interested in is 5,000 feet squared. Again, make sure you're answering the question. That's kind of a big issue that we have when we do the word problems. But again, pause the video at any time, go back if you need to. All the problems are obviously not going to be the same, and so another scenario that we would have is the one in example 2. But before we do that, this is kind of a strategy to follow, like go through the process, introduce the variables, draw a picture if you need to, figure out if you're maximizing or minimizing, which of the functions you're going to be using that's going to be maximized or minimized, and then write your formula. Then you can work your way through, take your derivative, set it equal to 0, make sure that it is actually a max or a min. And so in our next problem, we have a situation where we are going to be creating an open top box from a piece of cardboard. So the picture was drawn here. I'm going to cut out corners from each corner and then fold it up, so that when this length of 24 inches loses that corner and it gets folded up along the edge, it's going to lose an x on the left and an x on the right. So that's where we get 24 minus 2x. And the 36-inch length is the same thing. It's going to lose an x on each side, so 36 minus 2x. So when I'm setting this up, I want to make sure I have the maximum volume, which means I'm going to have to figure out what the volume is. Well, in this scenario, I only have one variable. So I can go ahead and set up my volume equation just by multiplying the length times width times height, or height times length times width, or however you do it. So my volume is going to be x times 24 minus 2x times 36 minus 2x. And the volume is what I'm trying to maximize, because I want to maximize volume. Now it says don't forget to consider the domain or reasonable values for x. That means when I get my x values that I'm going to use, I want to think about whether those are reasonable values or not. So I'm going to go ahead and work through this. I will start by simplifying b of x, and I'll multiply that all through. I'm going to grab a calculator so I can go through that. I get 24 times. So my first, I should get 864x. I'm just distributing through. I did x times 24 times 36. Now I'll do x times 24 times negative 2x. So that's minus 48x squared. Then I'll do x times negative 2x times 36. So that's minus 72x squared. X times negative 2x times negative 2x plus 4x cubed. I'll go ahead and simplify that. 864x minus, that would be 48 minus 48, let's see, 48 minus 72, sometimes I don't feel like thinking, minus 120x squared plus 4x cubed. And then again, what I'm doing is maximizing the volume, which means I have to take the derivative. So I get 864 minus 240x plus 12x squared. I'm going to set that equal to 0, and I'm also going to move this around. 12x squared minus 240x plus 864. And so this is what I'm going to be working through. And these are pretty big numbers. Most of the time I would say factor this. Well, I don't even know if this is going to be factorable. It might be, it might not be. So I always have that backup plan. I'm going to go way over here and use my backup plan. And I don't know if you remember this from your days in Algebra 2, but you could use, and even in algebra, you can use something called the quadratic formula, where x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a, where I have an a, b, and a c. And this is going to save me from having to try and guess and check with such big numbers. I can plug them in and get my x values. So in this case, x equals 240 plus or minus the square root of negative 240 squared minus 4 times 12 times 864, squeezing that in, all over 2 times 12. I'm going to let you guys go ahead and work through that. Again, pause the video, and then we'll meet back here, and we'll put that guy together and see how we compare with our answers. Okay, so welcome back. I got my values. I got x to be roughly 7.6. When I did 240 plus inside here, I got 126.996-ish. I got 7.6 for that one, and I got 4.7 for the other one. So now I'm going to do my V prime chart, and I'm going to do those test points. 4.7, 7.6. Again, remember it says don't forget to consider reasonable values for x. So when I do my test points, it doesn't make any sense for x to be 0. So I want to make sure I try something that's reasonable. Maybe I'll try 1, 5, 10. Do my test points. Those test points will go into this spot here, into my derivative. So if I do 1, I get 12 minus 240, which is going to be negative, plus 864, that's going to be a positive value. Then I'll plug in 5. I might have to use my calculator. 12 times 5 squared minus 240 times 5 plus 864. When I do that one, it comes out to be a negative value. Then if I try something over here like 10, I'm going to get 1200 minus 2400 plus 864. Let's see, or 10, yeah, 10, whatever. Okay, work through, give it a try. You should end up with a positive value, which makes increase, decrease, increase, and we end up with my max being 4.7. So what I have is 4.7 inch squares need to be cut. I want to double check and see what size squares should I cut out of each. I'm just going back to read the directions. What size squares should I cut to get the maximum volume? And so I did answer my question. I should cut 4.7 inch squares. So again, I'm going to ask you to pause the video, flipping the page over. You'll see they give a picture of it, and notice that this is what happened. So it's increasing and then it's decreasing. You notice that the max value there is when we hit 4.7 inches. Okay, pause the video again, give the next one a try, see how you do. Meet back in a little bit. Welcome back. I hope you had fun drawing that picture. Went through my box, did my dimensions, X, set up my volume, did my simplifying on the next level, worked my way down, and then took my derivative. Again, I went ahead and used the quadratic formula because I wasn't sure if it was even going to come out nicely, and the numbers were fairly big. So quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. Plugged it in, I got 12.7 and 3.9 for my two values. I should double check that one again. 200 plus 105.8 divided by 24. Yeah, 12.7 again. All right, so I took those values, did it in my F prime chart. I did find that it was increasing, decreasing, increasing, and so 3.9 inch squares were the ones that I wanted to cut out. All right, we are actually going to skip the next example and move on to example 4. It goes on to talk about unbounded or unclosed. This is when we're, in the previous ones, when we graphed the picture, we had this sort of upside down parabola. Well, what happens if I have these things that are endlessly growing on each side? Well, I'm going to find a minimum, so I'll be minimizing the next problem. Minimize, I set it up the same way. It's just that when I do my prime chart, I'm going to want a minimum value. So we'll get this problem set up, go through it, again, run through another sample of it, and then I'll let you guys work on some practice problems. So let's start. We have two pieces of information are given, and that is the fact that I have a volume of 216 cubic inches, and that I want to minimize the surface area. I want the minimum surface area. Again, the last couple that we did were maximizing, because this is a minimum. If you look down below at the graph, I'm not going to move my picture again, but I know you can see, you've got the notes in front of you. Notice that this is an upside down thing. You also know what our answer is going to be, the minimum surface area, and what the X value is. But let's go through and set that up and show how we find that. So the first thing that I'm going to talk about is the fact that the volume is 216 cubic inches. That means that x times y is 216, or I could write that as x squared y. But that isn't the function that I'm trying to minimize or maximize. I'm trying to minimize the surface area. And remember, the surface area is just all the little areas added together. So I'll set up a new function, S I'll call it, for surface area. You can call it whatever you want. And I have an x by x base, which is x squared. And then I have an x by y side, and another x by y side, and another x by y side, and another, actually, total I have 4x by y sides. The problem that I have, because the surface area is the function that I want to minimize, again, I do that by taking the derivative and setting it equal to 0, but I have this y in here, and so that's where that original equation comes into play. I can solve for y, and then I can replace y with this other looking function. So I end up with a surface area that is x squared plus 4x times 216 over x squared. And I'll just take a few moments to simplify that by multiplying 4 times 16, and then I can also cancel out the x's here. So 4 times 216, I get 864. Oops, I don't know why I wrote equals. Just thinking, I guess. Plus, it's 864 over x. Well, I talked about this before, and I don't know if you remember. It's not like you remember everything I say, but to take a derivative on this, which is what I'm going to have to do, to take a derivative on this, it's not going to be as easy as if I just rewrite that as x to the negative first power, and then my derivative is going to be easier to find. I can just do a power rule. So s prime is 2x plus negative 864, negative 864x to the negative second. And to me, it's easier to take the derivative with a negative power, but it's easier to solve with a positive power. So in my next move, I'm going to set this equal to 0, and then I'm also going to rewrite that as negative, or 864 over x squared to make my solving easier. So I just did a little bit of simplifying so that my solving is going to be easier. And I'm going to go ahead and add the 864 over x squared equal to 2x so that I can solve this. That means I'll multiply the x squared out, so that gives me 2x cubed. I will divide by the 2. 864 divided by 2 gives me 432 for my x cubed. And then I'm going to go ahead and take the cube root of that. Oops, I didn't slide my paper down. So I have to take the cube root of that. The cube root of 432. Now, they wrote it as 6 times the cube root of 2, which it is. But for what we're doing, I'm just going to go ahead and do the cube root and put it in as a decimal. And so the cube root, I can take 432 and raise it to the 1/3 power. Or if you have a cube root key on your calculator, you can do it that way. When you take the cube root of that, some of your calculators are actually going to give you that nice answer. It depends on the kind that you have. But my calculator gives me an approximation, and I get about 7.56. So x is roughly 7.56, and that's fine with me. I can use that. That's my x value. But now I want to find my surface area. What is the minimum surface area? Well, I have to take that value and I have to go ahead and plug it back into my surface area equation that I had up here, which is this one. I'm going to go ahead and plug that in. I get 864 over 7.56 plus 7.56 squared, or I could even just keep it as the cube root of 432 if you wanted to. Really, for what we're working on, that doesn't matter that much. I should be checking to make sure that this is a minimum S prime chart, 7.56, because I want to make sure that I have a minimum. And so when I do that, if I do my test points, I'll put it in this value. Like let's say I pick 1, that's 2 minus 864, clearly negative, decreasing. If I do something like 10, that's 20 minus, if I do 10 squared, so that'd be 8.6428, that's positive, so it's increasing. So this is a min like I wanted it to be. But to go back to my surface area that I'm solving for, my surface area would be the value I get when I evaluate what I just did here. So 864 divided by 7.56-ish, I'm just approximating, plus 7.56 squared. And my calculator is thinking. It's taking a long time to think. So 171.4-ish, 171.4, and that would be inches squared, would be my final surface area that I was interested in. So again, I had my connector, and then I had to set up the equation that I was going to minimize. we have one more exercise that is based on the very similar problem to the one that we just did, except for it incorporates measurements into it as well. And I'm going to hold off on that one as well. I want you to get comfortable. We'll work on the measurement incorporation when we get into or when we do our next set of notes. And so what I'd like you to do is give the problems that we just tried a try on your own. So in your packet, I'm going to assign your homework, and I just want to just direct you so that you kind of can look at these. I want you to do 1, 2, 3, 4, 5, 6, 8, and 9. So in your homework packet, 1, 2, 3, 4, 5, 6, 8, and 9 is what you're going to do for homework. Not the evens or odds like usual. I want you to do those particular problems. But just so you have to look back at, 1 and 5 are a lot like example 1, and very much like example 1. It's not a garden. I mean, I think it is still even a garden and a stone wall, okay? 2 is a variation of example 1, but a little bit different scenario, but still you're dealing with fencing an area. 3, 6, and 8 are identical to example 2. Except for they put that it's a store owner or a store manager wants to create the box. It's not just a general, but the same thing. So get the setup and go and get some practice with those. And then 4 and 9 are just like example 4. So if you need to go back and look at that, the whole setup is the same. They give you the volume, the volume of the square base box, and then you have to deal with the surface area, minimize the surface area. So go ahead and practice those. As always, if you have questions, let me know, and I will talk to you soon.